So we're in this chapter on reacting mixtures and combustion, and last time we talked about the balanced stoichiometric coefficients and the balance reaction equations, where we take fuel, we have air with the oxygen with it, goes to the hydrocarbon fuel, the carbons go to carbon dioxide, the hydrogens go to water vapor, and you have the nitrogen going for the ride. Okay, well now what we need to do is we need to consider energy balance, first law. After that, second law. You can do a second law analysis. The first law analysis for combustion is huge, very important. The second law is just something you can do, but not as important for this class. So think about a reactor or a combustor. You have what flows in, some fuel, and some, let's just consider air. You could have pure oxygen as well. And what goes out? Products. What are the products? Carbon dioxide, water vapor, nitrogen, maybe some uncombusted fuel, maybe some excess oxygen, but these are the primaries, those three. And what we want to do is we introduce a dashed enclosing. Hey, what did I just draw here? A little control volume, that's all. And then you say, I think I know how to do a conservation of energy for a control volume. The control volume can have some generic Q dot coming into the control volume as well as W dot out of the control volume. And we just write our equation almost from memory, having written it so many times for a control volume. The rate of change of energy stored in the control volume with respect to time. Only thing we're going to be doing is considering steady state, so that term is 0. And then that's equal to the rate at which it's flowing in with heat transfer minus the rate at which it's flowing out across the boundary of the control volume due to power. That could be electric, that could be shaft, that could be a lot of little things. But basically, a lot of times in our reactor, that's often almost always 0 as well. Almost always 0. All right, and then we're going to have our mass flow rate, and then we have the enthalpy coming in. So you have this this mass flow rate times the enthalpy coming in of each of the reactants, sorry. Let me move it over a little bit. So we'll have the sum over all of the reactants, the mass flow rate, and its enthalpy incoming minus this mass flow rate, enthalpy over all the products that are exiting. We pause and look at that for a minute. If we have, let's not strike the W dot term, let's leave it in there, the book leaves it in there. But does this equation look okay? What did we neglect? Changes in kinetic and changes in potential energy are negligible. The only thing is I probably want to write this on a molar flow rate basis, so let's do that. The sum of n dot h's with the h bar for each of the incoming reactants minus the sum over all the products of n dot h bar e. Let's go slow, make sure we understand everything. Why is there this R for reactants, P for products, I incoming, E exiting. The bar, it's on a molar basis for the enthalpy, so kilojoules per kilomole, and N dot is a molar flow rate. Molar flow rate. Okay, that's a lot of new symbols, and some of them really make sense, some of them can be a little tricky. Let's finish rewriting this equation. What I'm going to do is I'm going to put this right, I'm going to do this. I'm going to put Q dot and minus W dot control volume on one side, which means I need to change the sign right there. There's the good equation. I wanted to switch around a little bit. Okay, what we do for this is we think that we have our molar flow rate of the fuel. Okay, take the whole equation and divide by the molar flow rate of the fuel. And so you come over here, you got N dot F, you got N dot F, and then n dot f and n dot f. So this is like a lowercase q that we've studied before, although we don't introduce a new symbol for it. Let's just say it's q dot per n dot of fuel. So if you look at the units, it would be kilojoules per second divided by kilomole of the fuel per second, with the seconds canceled. So it's like how many kilojoules of heat transfer per kilomole of fuel. That's a very useful quantity. Okay, that's the units on that term. A lot of times what we'll do is we'll switch the order, so we'll have the sum over the products, and then we'll have this ratio right here, the flow rate of a particular product that's exiting divided by the molar flow rate of the fuel coming in. What is that? That's our stoichiometric coefficient. The book uses n without a dot for the stoichiometric coefficient, a general stoichiometric coefficient in our balanced chemical reaction equation. So right away it can be very confusing. Sometimes I have n dots, sometimes I have n dot of the fuel, sometimes I just have n without a dot. But this is a stoichiometric coefficient in our balanced reaction equation. Okay, so what we'll do is we'll put the n times h bar for each of those exiting products, and then no real color coding on this, I'm just mixing it up. Subtract the sum over the reactants of n h bar of each incoming reactant. Well, there it is. There is our, I can rewrite it, but there is our first law. What's the challenge? You mean that somehow there's a way to calculate the molar enthalpy of the product carbon dioxide and the product H2O, and maybe over here the reactant methane, CH4? But isn't the carbon sort of switching places? Maybe it started and it was in a compound with hydrogen and methane, but then after the reaction it comes out grouped with oxygen and carbon dioxide. That's a new problem for us. You know, basically we had steam in, steam out, refrigerant in, refrigerant out. But now we're conserving species, we're conserving our carbon, we're conserving our oxygen, we're conserving our nitrogen, but they're changing in changing group. And so that goes back to our chemistry. How do I put everything so I can get a common energy measurement for these switching around of the components? So there's our equation, and the challenge is explaining or coming up with that molar enthalpy, so everybody has the same measurement standard where it starts. Go back to our tables, or even chapter 3. There's a very good discussion about datum points. And in our steam tables, it's like our energy measurements started with the triple point of water, and I believe it was the saturated liquids, so use of F at the triple point, I may be wrong, I have to look at it, is set to be 0. And measurements go from there. And did you know that once you set the saturated liquids internal energy to be 0 at that point, you can get a negative U? It can be less than 0 for water. How can you get a negative value for the energy, the internal energy of water? How could you do that? Then the datum is set higher. So this is about 0 degrees C. I know it's the 0.01 degrees C. Make it go colder. Well, if you let it go colder, it turns into solid. It's ice. And ice often has a negative U, which is like, hey, how can that be? It's just your datum point. And when you talked about refrigerants, they said, well, what we're going to do is set the enthalpy of saturated liquid at a particular temperature. I think it's negative 40 degrees C, because that's also negative 40 degrees F. and it's very, very cold. And so they set that as 0. And they measured the enthalpy of, as well as internal energy, the energy of all your refrigerants from that point. Well, the same thing comes here. You have to have a common place to start measuring. And so they said, what we're going to do is we're going to talk about the standard reference state of 25C 1 ATM. And we're going to talk about stable elements at that standard reference state. And we're going to have them have like 0 enthalpy. So something like, well, let's just look at what they do here. Oh, I'm sorry. And then what they did was they were able to come up with the enthalpy of formation. And so this is how they expand it. So this will be then the departure from the enthalpy at 298 to whatever the enthalpy is at whatever temperature it's at. That's a change in enthalpy right there. So maybe it's a lot warmer than 25 or 298 Kelvin. And this really gets you that enthalpy of formation if it would form from stable elements at that temperature and pressure. So you're going to see these enthalpies of formation. Okay, let's take a look. Why do we have the bar on this on a molar basis? Why is there a subscript F on it? To remind you, this is enthalpy of formation. Professor, I'm confused. That's the enthalpy of saturated liquid. Relax. Different chapter. You have to look at the context. Correct? Yeah, sometimes that's very confusing. And then what about the naught up there? What does that indicate to us? Standard pressure, standard conditions. So we've seen that naught on a number of terms throughout the class. So where do we find this data for the enthalpy of formation? Well, into the table A25, and they list a pile of substances that remind us or give us the formula, and then they remind us or give us the molar mass, and then right here I truncated, I dropped the rest of them, but here's a column of the enthalpy of formation. Notice the units. The units are kilojoules per kilomole. And a lot of them are 0. Why are they 0? Because they're stable elements at those reference conditions. And so they're chosen to be 0. And then some others, like water and methane and propane and octane and blah, 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 they don't have 0 values. And we need those enthalpies of formation. Okay. The other thing to notice is there's 2 waters. What? Well, what is the difference in the description of those 2 waters? Just looking at it. One is G for vapor or gaseous, and one is, what is that, L for liquid. Why didn't they stay with F and G? Don't ask questions like that. That's confusing, isn't it? But hey, when you see it in parenthesis G, that means it's gaseous state. So look at all of these. Isn't this saying solid, gas, 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 gas? A lot of them are gases. But parenthesis S, that's like solid carbon. Okay. And then down here you have liquid, because when we buy gasoline, in what phase does it go into our gas tank? Liquid. Comes out of the pump. It's liquid like octane. That's how we would model. But if you're buying natural gas in a pipeline from CPS to burn in your home, how's it coming into your home? Not in the liquid state. It's coming in, methane's coming in the gaseous state. So water as well as octane can be, and a lot of other things, can be at 25 degrees C in the vapor or in the liquid state, so they have to be careful. These 2 enthalpies of formation are not the same, are they? And what do you suspect? That they're going to be related to the HFG, heat of vaporization, and the molar mass. That's what they are, between the 2 values. Okay. Because notice this, when we have the HFG, that was on kilojoules per kilogram basis, and so I'll use my molar mass to be like kilojoules per kilomole, and then that would be the difference. All right. So this table is very important. In this chapter, you have to go into that table and get those enthalpies of formation. So this is a problem. It reads, we have methane 25C, 1 atm. That's the standard conditions. That's nice. It enters a furnace at the standard condition. It's not coming in really hot or really cold. Standard conditions coming in. Operating at steady state. If we had a furnace not operating at steady state, we don't analyze any furnaces that are not in this chapter at steady state. It's all steady state. It burns completely, so there's complete combustion. You have 150% theoretical air, a little excess air, 50% excess air, and the air comes in a separate stream at 350 Kelvin and 1 atm. That's a little different because at 350 Kelvin, that's a little warm compared to 298. We're going to need to take that into consideration, our energy balance. It comes in a little warmer. The air does. The products of the combustion exit at 590. They come out pretty warm. And at 1 atm, kinetic potential energy effects are negligible. Determine the heat transfer. Now this is kind of funny wording, to the furnace from the surroundings. So there's our little combustor. This is our traditional sign convention for Q dot. And you look at it in kilojoules per kilomole of fuel, so it's divided by N dot of the fuel. That's what we're asked to solve for. And see, it's into, well, we're going to get a negative answer. Because this is a combustion, it's going to be transferring heat out. The products are coming out warm, but there's going to be some heat transfer out. Here's our answer to the problem. Negative 685,000 kilojoules per kilomole of fuel. That negative sign means that it's actually out of our reactor, or out of our furnace. Okay, how do we solve it? First step, what do we have to do? We practiced that last lecture. You must get a balanced chemical reaction equation. Those stoichiometric coefficients are key. We need those. So we come in with methane, leave a 1 there. And you do the carbon balance, put a 1 in front of that carbon dioxide. Do a hydrogen balance, you need a 2 there. You do the oxygen balance to find out that you need a 3 in front of the O2. And then the nitrogen coefficient, we work it out. Now, this may take you a couple lines to get there, but I encourage you now, if you know you're going to do an energy balance, get numeric values, single entities for those stoichiometric coefficients. Go ahead, because this will probably be like 3 times 3.76. Calculate it once, put it down there, 11.28. It'll be a lot simpler for the math. A lot of times, last lecture I had, oh, that's 0.1 times blah times blah. No. Once you figure that out, let's take the next step, get them single coefficients, single numbers for each of those stoichiometric coefficients. This is our energy equation that we derived or showed. It's in the textbook. This is 0, as it almost always is. This is what we're asked to solve for. So we have to sum over the products and then sum over the reactants. So let's do the sum over the products. So what I would do is I'd say, what's my stoichiometric coefficient, the enthalpy of formation, and then the enthalpy that the product is exiting at minus the enthalpy that it is the reference of 298. Everything's measured from respect to that reference. And so I have to write this for each of my products. I have to do it for carbon dioxide. I have to do the stoichiometric coefficient, the enthalpy of formation, the exiting temperature, enthalpy minus the enthalpy at 298. See that delta? That's compared to the 298, the reference temperature. Okay, and close. I have to do that for the H2O. I have to do that. This can be a little tedious. The first time you do it, you say, this is ridiculous. Come on now. Hey, once you do a few of these by hand, then you're really anxious to use a computer program, aren't you? This will be for the oxygen in the products, because it is one of the products coming out, as well as the stoichiometric coefficient, enthalpy of formation, the enthalpy of the temperature exiting minus the enthalpy of 298 reference. and this would be for the nitrogen. Now, because the nitrogen shows up on both sides, nitrogen shows up on both sides and oxygen shows up on both sides. Sometimes I'll even add a little extra, say, this is the oxygen in the products, this is the nitrogen in the products. And then we continue with the minus sign. So now we have minus the stoichiometric coefficient enthalpy of formation plus the enthalpy temperature coming in minus the enthalpy of 298 for what? This one would be for our methane, CH4, minus stoichiometric coefficient enthalpy formation plus the molar enthalpy at that incoming temperature minus the reference 298 for our oxygen. That's why sometimes I'll put oxygen coming in the reactants. See how that can be confusing? I have oxygen here, I have oxygen there. It can be confusing. So let's do that, leave it there. And then finish out this equation, minus the stoichiometric coefficient enthalpy formation plus the enthalpy at the temperature coming in minus the reference 298 for the nitrogen coming in the reactants. All right, so let's try and get these coefficients. What's this value right here? It's a CO2 in the products. What's that stoichiometric coefficient for this problem? This one right there, that stoichiometric coefficient. You have to look at your reaction equation. I'll clean it up, make it a little visible, more visible to see. These are my products. These are my reactants. CO2 in the product was the stoichiometric coefficient. 1. Yeah, if we got lost on that one, oh boy. Okay. How about stoichiometric coefficient, the water vapor in the products? 2. Right? All right, stoichiometric coefficient of the oxygen in the products. 1. And the stoichiometric coefficient of the nitrogen in the products. 11.28. All right, stoichiometric coefficient of the methane in the reactants. Well, this one's easy. We like to leave a 1 in front of the fuel. It's very, very, very rare. Leave a 1 in front of the fuel. In this case, the fuel is methane. Stoichiometric coefficient from the oxygen in the reactants. 3. See, this is confusing. They say, hey, we already did the coefficient for oxygen. Yeah, but this time it's in the reactants. Okay, and then a nitrogen. Well, this one is, nitrogen is not undergoing a reaction, so it came in 11.28. Stoichiometric coefficient goes out 11.28. All right. All right, okay, for the methane, the temperature coming in for the methane is 298, so the difference here cancels. The delta H for the methane cancels for the fuel. But for what comes in for our oxygen, it came in at 590. It came in at 590 for the nitrogen. So you have to go to our gas tables, get the molar enthalpy for the oxygen at 298 and at 590. I think I have a table for that. Next slide. Let me look. Okay, I have it over here. This is table, what is that, A23. You have the carbon dioxide, the molar enthalpy as a function of temperature. You have the carbon monoxide, molar enthalpy as a function of temperature. Water vapor, molar enthalpy is a function of temperature. Here's our oxygen. And so we were looking for 298. There's the 298 right there. So we come over here. We need this value right there. Okay. 9,904. And then we needed it at 590. Is that what we said? And it's the difference between these two values for that delta H, just for the water, or just for the oxygen. Which one was I doing? I think I was doing the oxygen. I'm sorry, I got off. I need it for the oxygen and I need it for the nitrogen. True? Yeah, that's what I need. Okay. So we just talked about getting these two values out of the table. Okay. How about our enthalpy of formation for that oxygen? Where do we find that? I think it was in this table. And so our oxygen enthalpy of formation is 0. And then once you do this a couple times, it's like, yeah, it's happy oxygen, happy nitrogen, so those enthalpy of formations are 0. So this is 0 and this one is 0. Okay, let's continue on. I need the enthalpy of formation of carbon dioxide. We get that from our table. Carbon dioxide right here. Enthalpy of formation is negative 393,520. I'll show you something. When we go to this table right here, they put a little reminder for the carbon dioxide. What do they put right there? Negative 393,520. That's nice when the data is repeated. Not too much data gets repeated, but some data is repeated. So you could just look at this table and get the enthalpy of formation of the carbon dioxide. You get the enthalpy at 298. And then what temperature did it go out at? I forgot. Oh, 590. Oh, it was 350 coming in for these guys, not 590. This is 350, isn't it? This is 350 coming in. So I botched that too. Man, I'm making too many mistakes. So for the 350, where's 350? This is 350. So for the incoming, we need that difference for the nitrogen and for the oxygen. For the outgoing, the products, that's the difference and the difference for both the oxygen and nitrogen, because we have both of them in the products. Okay. All right. So carbon dioxide in the exiting products of 590. So likewise is delta T, delta H bar, I mean. For water vapor, delta H bar. The oxygen, delta H bar. The nitrogen, delta H bar in the products. This enthalpy of formations are 0, 0. This water, you have to pick. How does it go out? At this point, when in doubt, it goes out at 590 Kelvin. It's going to go out in a vapor state. It's not going to condense. It's not close to the dew point temperature. You have all the tools to check the dew point temperature to see if any condenses, but it won't, not at that temperature. Okay? So, here are the numbers. So we had that enthalpy of formation, 590, 298. For the carbon dioxide, we look up the enthalpy of formation, carbon dioxide, those two enthalpies, the water. This gets a little tedious, but you got to get good at it. Okay? Fair game for the exam. I sure wish we could use computers on exams. Yeah, me too sometimes, but that's just the nature of the beast. So all the stoichiometric coefficients, hopefully they make sense. All the enthalpy of formation, some of them are 0. Others are out of the tables. And then you have the changes in enthalpy, change enthalpy, change enthalpy. And then you just do the math correctly and you find out negative 685,000 kilojoules per kilomole. Negative meaning it's not into the reactor, but it's exothermic. Heat is coming out. First law analysis. So let's press forward. we have our conservation of energy equation for reacting mixture. We can also rewrite this equation after you solve a few of these because you're always looking up enthalpy of formation, enthalpy of formation. Let's sort of group those into this one term called the standard enthalpy of combustion. So all of these enthalpy of formations with the coefficient, stoichiometric coefficients, would make sense for that reaction. Now, often if you just have a particular fuel like methane, CH4, with 100% theoretical air, then the stoichiometric coefficients are known. But as soon as you start playing and you say, oh, it's 120% air, and then it's 150% air, well, then it does change the coefficients, especially in the products, because you get some oxygen out. But anyway, this is very common where they will report the standard enthalpy of combustion for a fuel, assuming just perfect amount of air. Right? Okay. So then you can pull those terms out, have this term by itself, and then you'll just have, did the product go out hot compared to 298? Then this term is non-zero. Do any of the reactants come in hot or cold compared to 298 Kelvin? Then this term. So often our reactants come in at 25 degrees C, this whole thing is zero. That makes nice, a little easier. And this enthalpy, standard enthalpy of combustion for 100% theoretical air can be calculated, tabulated once, and put up in a table. All right. So calculate the standard enthalpy of combustion. Hey, what was the symbol for that standard enthalpy of combustion? It was some H bar, because it's on a molar basis. That is very funny subscript. Was it RP? Rest in peace? What does this RP subscript indicate? Going from reactants to products. It's just, there's notation. Look back here. What is the notation subscript? RP. How would you interpret it? Going from reactants to products. And then there was this naught. What does that mean? Standard conditions, just 25C, 1 ATM. All right. So what you do is you're thinking all of the reactants come in at standard conditions, 25C. All of the products go out at 25 degrees C. You do an energy balance. And you find that the Q dot per N dot of the fuel is equal to the standard enthalpy of the combustion. Let's take a look at our equation again. Not that part, this part right here. No work. If they come out at 25, come in at 25, this is it. And so there's a formula again, sum over the products of the stoichiometric coefficient, enthalpy of formation. Sum over the products. Standard formation minus the sum stoichiometric coefficient enthalpy formation over all the reactants. Now, if you take a look, this one has an enthalpy formation of oxygen is 0. This one and this one, enthalpy of formation of nitrogen is 0. The enthalpy of formation oxygen 0. So this one's 0 as well. So basically, the products, what you'll get is 1 times the enthalpy of formation for CO2, and you'll have 2 times enthalpy of formation for the H2O. And again, there's a choice. Do they come out vapor or gaseous? This problem statement says H2O goes out gaseous. So put a G on there if you really want to emphasize it. And then we have minus the 1 for the fuel, enthalpy formation of the CH4, and it's going to be gaseous as well. So you just pick up 3 values out of the table. Okay. When you do that math, you come in at, what is that, negative 802,310, meaning that's how much heat would be coming out of my reactor per kilomole of fuel if the products and reactants came in and out at the same temperature, standard 25 degrees C, and there was complete combustion with stoichiometric air. Yes?
Sorry, sir. Could you repeat one more time why the oxygen goes to zero?
Oh, the enthalpy of formation of the oxygen.
Yeah.
Yeah, why? They picked stable elements. Let me see if I can find that. Well, first of all, it's in the table right here. So the carbon, the hydrogen gas, the nitrogen gas, and the oxygen gas, in these forms, all have zero enthalpies of formation. So, but the people, the geniuses that worked this all out, decided these elements are going to be set to zero. Basically said that, let me see if I can find it, stable elements at the standard reference state are set to have a zero enthalpy. They're chosen. Just like the enthalpy of refrigerant, saturated liquid at negative 40 C is chosen to be zero. I think a lot of the chemists worked this out years and years and years ago. All right, so this was the calculation in detail. And so we noticed that the enthalpy formation of oxygen and nitrogen and the oxygen, well, first of all, oxygen and the reactants, but the, why do I have oxygen in the products? This is not right here. 1, 2, 3, 4. Is my equation balanced? Doesn't look like it, but with standard methane, hold it. Do I have an error here? Let's do the carbon balance. That's a 1 right there. Do the hydrogen, there's a 2 right there. That's 2 plus 2. I need 4. This is a 2. Sorry. That's a 2. What's 2 times 3.76? I think I copied this wrong from some other source. So 2 enter 3.76 times. That's 7.52. So I'll fix that. 7.52 on the nitrogen, 7.52. So, but it really doesn't matter the wrong coefficient here, the wrong coefficient there, because the enthalpy of formation for the oxygen and nitrogen are 0. And I did get the right coefficients in front of the carbon dioxide, in front of the water, and in front of the fuel. So these are the 3 participants. So the final answer is still correct. All right. When computing the standard enthalpy of combustion, isn't that HRP bar not? It matters if the fuel is liquid or gaseous, true or false? It does, it's true. Because that affects the enthalpy of formation of my fuel. And you remember liquid octane, gaseous octane? Yeah. When computing the standard enthalpy of combustion, it matters if the oxygen is from pure oxygen. Maybe you're NASA, you spend a lot of money, get pure oxygen. Or the oxygen comes from air, true or false? It doesn't matter. It doesn't matter if there's nitrogen in the equation or not. If we go back to this equation, we say, there's no nitrogen in this equation because the oxygen's coming from pure. Well, the O2 as well as the N2 have 0 enthalpy of formation. That's the same thing. I made error in the stoichiometric coefficients, but they were multiplied by 0 on the oxygen and nitrogen term. When computing standard enthalpy of combustion, it matters if the product, the water vapor, or the water goes out as either liquid or gaseous. Does that matter? It does. And if we go back to this example, here it is for water, but that's the one for H2OG. If you look, there's a different enthalpy of formation for H2OL. That's how it'll affect it. So this one is true. It matters. the standard enthalpy of combustion of liquid octane is the same as gaseous octane. True or false? False. They have a different enthalpy of formation. The standard enthalpy of combustion for a fuel is higher when combusted using pure oxygen than when using air. True or false? False. Professor, you just asked the same question twice. I know, I reworded it, the same concept. The standard enthalpy of combustion doesn't depend on the state of water being either liquid or gaseous in the products. This is a double negative. This is a bad question. It does depend on it. So this one is false. It's a double negative. These are really hard. They should be thrown out, shouldn't they? Yeah. That's a bad question, sorry. Heating values. If you go and you take a look, you can figure out what's the heating value of particular fuels. They'll be kicked around, and so these are tabulated in the table A25. Look way over here. There's a heating values, but look at it. It looks like there's two columns of numbers. Yeah, there's two columns of numbers. You have the lower heating value, abbreviated LHV. I wonder how that came out. Lower heating value. Pretty simple. Engineer did that. Not too clever. And then the higher heating value, HHV. Notice the units on them. They're in mass. It's kilojoules per kilogram of the fuel. So you can look over here. Let's say methane, because we played with that a while. You have the heating value for higher heating value and the lower heating value. Why do they have two heating values? What is the difference between these two heating values? Well, first of all, this guy right here is higher, okay. It's a measure of how much heat maximum you could get out of combusting that fuel. Theoretical error. So if you want a lot of heat out of your reactor or combustor, and I know this is a positive Q in, so a large negative Q dot over N dot, tell me a little about the temperature of the products that you want going out. You want them to go hot out? If you wanted a large Q dot, would you want the products to be hot, or would you want the products to be 25 degrees C? So they're going to come in reactants. They're going to have this chemical changing to carbon dioxide and water. And the question is if you want a lot of heat out of that furnace, you're burning methane, natural gas in the middle of winter to provide heat into your home. You would like a lot of heat put into your house. Wouldn't you like a large negative Q dot over N dot of the fuel? Yeah, you would like a lot of heat out. So basically this higher heating value is all of the products go out at 25 degrees C. You know what? For lower heating value, all the products go out at 25 degrees C as well. And then why do they have two values? See, it's your maximum heating value. And once I say it, it'll be obvious, but what is coming out in our products? Carbon dioxide, water, nitrogen. One of these could be a liquid at 25 C, the water. And so they kind of push it to the extreme. They say, look, all of the water goes out vapor, or all the water goes out liquid. Okay. If all of the water goes out liquid, which is it? Will that give you the lower heating value or the higher heating value? This is really hard concepts. It'll give you the higher heating value. If the water, H2O, goes out in the liquid state, it'll give you the higher heating value. And if the H2O goes out in the gaseous, that's really a lower heating value. Now, in our homes in San Antonio, we just have standard furnaces. You burn natural gas, and what goes out the flue? Pretty warm exhaust products, right? And so out it goes. If you're around a home that has a little pipe coming out of the roof from the furnace, and it's a really cold winter day, you look around the neighbors and it's like, oh, they have steam spewing out that little tube, that little pipe out of the roof. Well, what's happening is a lot of water vapors coming up, hits that cold air in the cold winter day, and then you get that wispy white condensate. I know we don't have enough winter days for us to make these observations. I wish we had more, but here you go. Hopefully that resonates. Maybe you've seen that. Maybe you've lived up north. You see it a lot in the winter, especially when it's really cold out. These homes are wisping out white cloud, out the pipes, typically out the attic. All right. Well, anybody lived up north, Chicago? Anybody that lived up there? One person. Okay. 2 people, 3. Right. The long winter, right? You want to get as much bang out of that expensive fuel that you're purchasing. You want as much heat into the house as possible out of that furnace for that fuel that you're burning. Also, the homes get very dry. So no sense sending water vapor out the flue, out the exhaust. So they have things called condensing furnaces. First time you hear that, that doesn't make any sense. You're going to condense inside a furnace. A furnace is hot. What are you doing? Does that resonate? Anybody heard of that? Condensing furnace? They pay a little extra for that. They want that exhaust to go out so cold, 25 C, like the air temperature inside your house, that a lot of that water condenses and then it just is back into the home. You're not sending a pile of water vapor out. Try to keep it inside the home. I know it's going to be liquid, but then it's not. It's going to go back into the gaseous state inside your home. So you can look it up. Look up condensing furnaces. What they're trying to do is they're trying to get not what is this? Not 50,000. They're trying to get 55,000. Let's say somebody says, "Honey, I just got a pay raise. Last year I was making $50,000 a year. This year I'm making $55,000 a year." Do you think that's a big pay raise? Yeah, I'd be excited. I'd go out and eat too. I'd celebrate. Don't worry, you're never going to get a pay raise like that. But this is a big deal, so that's why they spend the money, and engineers have designed condensing furnaces to try to get as much heat out of that expensive fuel into the home as possible. First time you hear it, it doesn't make any sense. But that's why they have heating values, both of them reported. All right. All right, how do you calculate maybe this lower heating value? Starting from the standard enthalpy of combustion. Here it is for burning methane. That's our standard enthalpy of combustion. Well, you need to use the molar mass of the fuel, which is 16. Do you think you could take this number, that number, figure out how to manipulate them to get this number? Sure. It's not that hard, is it? So doesn't it look like the negative of the standard enthalpy of combustion divided by the molar mass of the fuel? And that will give us our, if this is for the products, the water vapor going out in the vapor state, this will give us the lower heating value. So anyway, this is our product going out vapor, in water going out vapor. Divide by 16.04, get rid of the negative sign, and you get, for our numbers, 50,019. Well, you compare with table A25. Here's table A25. 50,020. Oh, that's too good of agreement, in my opinion. Come on. 4 significant digits, almost 5. I know some of you students were in Thermo 1 and statics giving me answers to 7 significant digits, which was impressive. But this is incredible that these calculations give that good of agreement. Let's continue. Okay, the heating value is the negative of the standard enthalpy of combustion divided by the molar mass of the fuel. Yeah, that's the equation. Sure is. When computing the heating value of fuel, it matters if the fuel is liquid or gaseous. Will liquid octane have a different than gaseous octane, a different heating value? Yeah, it will. Yeah, if you have your tables, you can look that up. How about computing the heating value for a fuel? It matters if the oxygen is from pure oxygen or from air. Does not matter. So that does not matter. When computing the heating value for a fuel, it matters if the water in the products is liquid or gaseous. Yeah, you get the lower heating value if it goes out vapor, the higher heating value if it goes out liquid. So that's true. Good? You ready to press forward? This is the part that I really, really like. Adiabatic flame temperature. A lot of us have used things to make things hot. Maybe a propane torch, maybe cutting torch, maybe acetylene, welding, cutting. Anybody ever used something like that? One person, two people. Yeah. Hopefully in the machine shop, when you do that machine shop experience, they do a little welding or even a little cutting torch. That sure would be fun. We're trying to get that in there, but good luck. I should give up trying to improve the curriculum. Just say, students complain about labs. Students can perpetually complain about labs because they're too hard to improve. Maybe that's what I should do. I feel like I'm pushing a rope. You ever push a rope? You're like, don't work. It really don't work. There's battles every level. It's like, come on, make a decent lab. Let them weld a little bit. Let them use a cutting torch as well as the lathe and the mill and the drill press. That would be great. But anyway, this class explains something about the adiabatic flame temperature. We can use the tools in this class to predict adiabatic flame temperature, different fuels. Well, okay, think about this. Temperature, I understand. Flame, oh, I got a visual image. Yeah, that's the flame. And it's adiabatic. What's that word mean, adiabatic? Adiabatic, what does that mean? No real heat transfer. So what happens is if you have a little, let's do it like this. If I have the air and the fuel coming in and there's some combustion and then it's coming out, the products are coming out, this is insulated Q dot equal to 0. When it's insulated, you get the highest temperature out of the products. That's our adiabatic flame temperature. Different fuels have different adiabatic flame temperatures. Some are really hot. Some are not so hot. And you just need to use them to get that experience. You ever try and do anything with propane compared to acetylene? Or even MAP gas? You can buy MAP gas at Home Depot and Lowe's. They're hotter. Okay. So you start with our energy balance equation. You say no work for sure. No heat transfer, adiabatic reaction. So what does that force this delta H of the products to do? Go way up. And so what you end up with is having an exit temperature which is unknown. But you can use this equation to solve for that exit temperature, that adiabatic flame temperature, where the enthalpy of formations and the incoming conditions, this is all standard. This would be 0. You report it for your fuel all coming in at 25 degrees C. So here's propane, blah, 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 100% theoretical air. What you do is you say, what happens if the products come out at 25 C, room temperature? You get a huge heat out of that combustion chamber, right? Let's say they come out a little warmer, 1,000 degrees. Well, you get lower value in magnitude for the heat out of it. You just keep playing this game until the temperature adiabatic flame, that Q dot divided by N dot is equal to 0. First time you do that, it's a little conceptually difficult. How am I using these equations again? Just as I tried to explain. Drive it such that Q dot over N dot is equal to 0. You're going to end up needing to go up to 2,000 degrees C, 2,394 Kelvin for propane from our calculations, from the data in our table. You have to do a little interpolation for that last one, right? Because there's not a line with 2,394 Kelvin to get those H's. But you can drive that to 0. What I typically do is I try and encourage students to bracket it and then do a linear interpolation for one and refinement on the adiabatic flame temperature. So try and do this Q dot over N dot, get rid of the negative sign. It's huge if the temperature of the products is low, maybe 298, maybe 1,000. This is a good one right here. We got the data. Look at 298. It's at 2043990. All right, at 1,000. So this is a point. At 1,000, it's 1436415. I want you to do this. Pull out your calculator, do a linear extrapolation, and give me an estimate of what temperature, this is a plot on the x-axis, what temperature, it will be 0. And this is really accurate. And then you can compare it with this one, which is running with all the numeric values inside the tables. The values are temperature dependent, some non-linearity in the specific heats, but often they're linear enough that you can get a pretty good estimate. Why do I ask you to do this? Well, when I'm teaching statics. All right, how many people remember, let's say this is X and this is Y. It's easier to maybe to remember your formulas like that. And you say Y minus Y1 divided by Y2 minus Y1 is equal to X minus X1 divided by X2 minus X1. Kind of like, I'm going to do a linear interpolation in X, and it's a linear interpolation in Y. This is a very similar equation used. It's just like Y is equal to mx plus b, but you avoid maybe the intermediate step. You're going to calculate m and b anyway, but here you go. So I'm really interested in my Y1. Let's pick this one to be the Y1 right here. So this is my 2,043990. That's 2,043990. And then over here, my Y2 is 1436415. So this is 0.2, this is 0.1, right? And then what's my X is 298. 298. What's my X2? 1,000. And so what do I want my Y to be for the, I know it's extrapolation, but it's a linear equation. It'll work. Interpolation as well as extrapolation. I want this to be 0. I only need to solve for X. I think that's what you had. Yep. How many people were doing it this way similarly? Yep. So basically, it'll be, how do I want to write this? It'll be X is equal to 298. All right. Then I'm going to have plus 2043990 times 1,000 minus 298 divided by 36405 minus, I didn't leave enough room, 2043990. Right? No? Did I mess up the algebra? I want to solve for this X, right? So maybe I should have wrote it like this. X is equal to X1 plus, or subtract Y1 times X2 minus X1 divided by Y2 minus Y1. Did I do the algebra there right? So did I make the error here negative? No, I think, what did I do here? No. It's what? Yeah, because in the denominator there's a negative. So that, yeah. Okay. What did you get? 2659. All right. Who's the next volunteer? Did you get one? What'd you get? 2668? 58 or 68? 58? 78. Well, it's all rounding off. Oh, that's fine. 298. This is 298, right? All right. What'd you get? 2659. Another volunteer. What'd you get? 2661. 2361. Do you see anywhere where you went?
I think as long as you're interpolating, which is between two numbers, I don't know if that's messing you up.
No, it won't. It's a straight line. I mean, I think you did the slope, didn't you?
Yeah, I found the slope, and then I get that number before adding the 298. I didn't add 298.
Okay, add 298 to that. Guess what? He's a genius. I should have saw that. Right? What do you get?
2659.
Very good. All right. So where are we at for time? It looks like I got about 4 minutes left, right? So this is the adiabatic flame temperature. You know what? Using our tools, we can go out to the internet or textbooks and we compare with reported values. What did we just do? Propane with air. And we just got the adiabatic flame temperature not to be 1980, but the adiabatic flame temperature to be 2,120. You say, oh, that's a big difference. Well, but read the textbook. It explains that these are experimentally measured, empirical. They measure it. And we have sometimes some incomplete combustion in the flame. You have some excess air a little bit, but really you do have some radiative heat losses, and you do have some dissociation of products. It doesn't always perfectly go to H2O and CO2. So that's an explanation for the difference. I think we're done. We won't cover entropy today. Thank you for your attention.